Integration has a wonderful variety of uses, but the best and easiest way for us to introduce it today is going to be as a means of finding the area between some red function and the x-axis, also referred to as the area under the curve. So, in our first example here, if we're tasked with finding the area under this red curve on the interval shown, it's fairly straightforward. The function is a constant, so it results in a horizontal line segment, and the area underneath it can be perfectly calculated as the area of this blue rectangle. So all we need to do is the height times the base, and we have our area. In our second example, the shape under the curve is slightly more complicated, but still nothing we can't handle. This red function is linear, so the area underneath this curve can be perfectly calculated as the area of this blue triangle. All we have to do here is 1/2 times the height times the base, and we have the area under this function. For our third example, the shape under the curve gets significantly more complicated, but we can certainly attempt it by using the tools we have so far. This area definitely won't be covered by a single shape, so we can try to throw down a handful of rectangles and triangles here to calculate the area. But we find that because of the rounded nature of this shape, we'll always have gaps. While this may seem like a roadblock, it's one that other people much smarter than us figured out how to work around, so we can follow their method. We'll still attempt to combine the areas of polygons to find the area under the curve, but to make things easy on ourselves, we'll use a handful of rectangles exactly as tall as the value of the red function on their left corner, which we'll denote with f of x. And in order to really make the math easy, we'll make all of them the same width, which we'll label as delta x. This way, there are clearly still gaps that make this approximation inaccurate, but we can really easily calculate this approximation of the area by saying it's the area of each individual rectangle added together. The area of each rectangle can be calculated by their height times their base, and we can simplify this formula by using the summation symbol, capital sigma, which basically just means add them all up. Now, in order to make our approximation more accurate, we'll simply double our number of rectangles. By doing this, we're now adding up twice as many rectangle areas, but the uniform width for each rectangle is now half as wide in order to fit them all. As you can see, the size of the gaps has shrunk considerably, but it's still not perfect, so we're going to add even more rectangles. Now, the width of each rectangle, delta x, is even smaller than before, and the approximation is visibly even more accurate. It's clear that by having any finite number of rectangles to cover our area, the approximation will always be imperfect. So, in order to calculate the exact area under this curve, we'll just have to work with an infinite number of rectangles. In doing this, it's clear that there are no longer any gaps or imperfections of our calculation of the area under our red curve, but in order to communicate what exactly we need to calculate, we need to change our notation. The height of each infinitely skinny rectangle is still the height of the function at that point, so f of x can stay the way it is in our formula. By including infinitely many rectangles, we have made each of them infinitely skinny. So, in order to denote this infinitely small width of each rectangle, we change our notation from delta x to dx. Lastly, we need a way to communicate that we are adding up infinitely many, infinitely small things. And lucky for us, there's a symbol that means just that. The integral symbol is used to replace the summation symbol, as it simply tells us to add up infinitely many of these really tiny parts. And this makes sense because it's literally just an elongated s for summation. So, in summation, when writing out the integral of a function in this manner, one of the ways it can be interpreted is as saying that we want to find the area under this function by adding up infinitely many, infinitely small slices of the total area.